Hello there, folks. Root Beer here, looking at more of the 2006 Fermat paper. That's the grade 11 multiple choice paper, and we are on question number 7. Okay? Hopefully you've taken a look at question number 7. Let's dive in here together. What is the smallest positive integer p for which the square root of 2 cubed times 5 times p is an integer? So we need 2 cubed times 5 times p to be a perfect square. Because then I can square root it and I'll get an integer. Okay. So we've kind of got two options. One thing we can do is we only have 5 possibilities. That's the advantage of looking at a multiple choice contest. Okay? There's only 5 possibilities. You can start eliminating some of them and go from there. Now they're asking us for the smallest positive integer, so I would start by asking, well, 1, that's the smallest of these possibilities. What if p is equal to 1? Do I get an integer? And if you got a calculator, that's not hard to work with. And you'll find that doesn't work. So then you would try 2, and then 5, because there's no point in trying E20, because if that works, great, but maybe one of these smaller ones does. So as long as we're thinking about this in a smart way, this won't take us too long. We got our calculator handy. Just trying each of these possibilities will get our answer. But if we wanted to do it more mathematically, more exactly, and with a bit more logic behind it, as though maybe we weren't trying to do a multiple choice contest, maybe we're trying to do a written contest. How would we do it then? Okay, because we want to prepare for really all contests. Well, what would we do then? We need to get 2 cubed times 5 times p to be a perfect square. And you'll notice that we've got 2 cubed and 5. Well, this is really 5 to the 1 here. And these guys are prime numbers. So this is prime factorization. You can write any number you want as a unique product of prime powers. 36 is 2 squared times 3 squared, for example. Okay? And when you start writing your numbers out like this, you start to make the connection that you're only going to have squares, for example, when all the exponents are even. Well, I have odd exponents here. Okay? 9 is a square, 3 squared. 27 is not a square because 3 isn't an even number. So I need to get even numbers here. I need the 2 to at least the 2 to the 3 to become at least 2 to the 4, and I need the 5 to at least be 5 squared. So I need a factor of 2 and of 5. Okay? And automatically that eliminates 1, 2, and 5. These don't have a factor of 2 and of 5. 10 does. And if we check 2 to the 3 times 5 to the 1 times 10, well, that's 2 to the 4 times 5 squared, and that's going to be a perfect square. Specifically, it is the square of 20. And if you were to try E20, you will find you actually get 2 to the 5 squared. And that 2 to the 5 is an odd exponent. That wouldn't be a square either. So really the only possibility, not just the smallest positive integer p, but the only one of these possibilities that gives an integer out is 10. Okay? So if you haven't seen unique factorization before, there it is. And our answer is going to be C10. And that finishes off question number 7. Join me for question number 8 in the next video.